Hello everyone and welcome to another lesson. So today we will be talking about continuous probability distributions, and this is chapter 6. So first and foremost, let's have a look at the learning objectives for today. So first, we will be computing probabilities from the normal distribution, how to use normal distributions to solve business problems, using normal probability plot to determine whether a set of data is approximately normally distributed, normal approximation to binomial distributions, computing probabilities from the exponential distribution, and finally computing probabilities from the uniform distributions. These 6 will be our learning objectives. Right, let's move on. Before we move on to continuous probability distributions, let's have a quick understanding about what a continuous random variable is. So in our last lecture, we talked about discrete random variables where we assign discrete values to a particular random variable. In a continuous random variable, we assign continuous values. That's why it says that can assume any value on a continuum. So for example, thickness of an item, continuous. Time, temperature, height, all of these have continuous values assigned to them. So that is why the thickness of an item, time required to complete a task, all of these are continuous random variables. Of course, this all depends on the ability to precisely and accurately measure it, right? So according to how you measure it, it depends. So today's lesson structure, we will be having a look at normal distributions. Then we will be talking about uniform and exponential distributions. And finally, we will have a look at the normal approximation to a binomial distribution. So if you remember, we talked about binomial distributions in our last chapter under discrete probability distributions. So first and foremost, let's have a look at normal distributions. Right, so under normal distribution, we will have a look at 4 sections. So first we will have a look at normal and standardized distribution. Then we will look at finding normal probabilities, finding the value of x when the z value is given, and finally we will have a look at what this normal probability plot is. So let's have a look at this normal distribution and what a standardized normal distribution is. So a normal distribution is bell-shaped, symmetrical, and the mean, median, and mode are equal. So something similar to this graph here. So in this case, you see that the mean, median, and mode are all equal, and this represents your standard deviation. And if your mean, this mu value changes, the location of the graph changes. And when your sigma changes, if sigma increases, the curve flattens, and if sigma decreases, the curve slopes upward. So the normal distribution density function is given by this particular equation. Now you do not need to remember this, but what we are focused upon is this particular equation over here. This is what we are interested in, but this f of x gives you the density function. So this is basically the normal distribution shape. As you can see here, if you compare the blue line and the yellow line, both these normal distributions have the same mean. However, sigma is different. For the blue line, sigma is higher compared to the yellow line. So in the case of the purple line, you can see that mu is greater compared to the other two that we discussed. However, sigma is also greater. That is why it is more flattened. So that's what's being mentioned here. So when you change your mu, the distribution shifts either to your left or to your right. And when you're changing your sigma, that is your standard deviation, when you increase it and when you decrease it, your spread changes. So now we've been talking about the normal distribution. Let's have a look at this standardized normal distribution and what it means. So any normal distribution can be transformed into the standard normal distribution. So what do we do here? What we are doing here is transforming these x units into z units. And what is this z? That's what we have to understand. An important fact to keep in mind: in a standardized normal distribution, the mean is 0 and your standard deviation is 1. So let's see how you translate this. How do you translate from x to z distribution? This is the expression. This is the same expression which I mentioned before in the density function. And when you're given the x value, you deduct the population mean and you divide it by the population standard deviation in order to get the corresponding z value. So the standardized normal distribution is also known as the z distribution, where your mean is 0, your standard deviation is 1, and it's given by this graph where your x-axis is now given by your z values and the mean is denoted by 0 and standard deviation is symbolized by 1. So the values above the mean provide you with a positive z value, right? So the values to the right of 0 gives you positive values, to the values to the left of 0 gives you negative values. So let's have a look at an example. If x is distributed normally with mean of $100 and standard deviation of $50, what is the corresponding z value for x equals $200? So simply we go and substitute these values to that equation. What is z? Z is simply you take the x value and you deduct the population mean, which is $100, and you divide it by this population standard deviation, which is $50, which gives you an answer of 2. Now you might ask, what does this 2 signify? How do you interpret this value of 2? Well, what this says is $200, the x value of $200 is 2 standard deviations above the mean of 100. Now we are dividing by the standard deviation, so we get the answer as 2. So how do we say it? It is 2 standard deviations above the mean of 100. That's how you interpret this value of 2. So if you get 0, that means you have 0 standard deviations above the mean of 100. In order to get 0, x has to be equal to mu. Right, let's compare these x and z units. So when you're given the graph, it's very simple. It's either you scale it in x terms or in z terms. So if you have scaled it in x terms and you get this bell-shaped curve, you have a normal distribution. So let's take $100 and $200. Now you want to have a look at the standardized normal distribution. So the same distribution, except for the fact that these values are now scaled. So $100, the corresponding value is 0. That is your mean value in a standardized normal distribution. And the corresponding value for 200 is 2. Z equals 2. Your mean is 0 and your standard deviation is 1 in a standardized normal distribution. Right. So let's have a look at the second area of this normal distributions, which is finding the probabilities pertaining to normal distributions. So probability is measured by the area under the curve, right? So we have the curve like this. If you want to figure out the probability of some point X lying in between A and B, what you simply do is you find the area under the curve. Now in this case, you would notice these two are equal, right? So probability of X lying in between A and B, right? You have the equality sign here. However, that is not present here. Why is that? That's because of this particular reason. The probability of any individual value is 0. So the probability of X being equal to A, right? The probability of A, that individual value is 0. And the probability of X equaling to B, that individual value is 0. Therefore, that is why these two are equal. So what are we talking about? We are talking about finding probabilities, right? For normal distributions. What do? We simply find the area under the curve. So the total area under the curve is 1. That is, the total area means the total probability. The total probability adds up to 1. And the curve is symmetric. That also we know because we are talking about normal distributions. We said it's bell-shaped, symmetric, likewise. So since it's symmetric, this curve divides it into half and half. That is something like this. So the bottom half gives you the values pertaining to X from negative infinity to mu. And the top half gives you the values of X, the probabilities from mu to infinity. So these two values provides us with a probability of 50% each, which adds up to the total probability of 1. Now, you might get confused as to how you get negative infinity here, because you have the y-axis here. But remember, where these two meet, that point is not 0 because I have not even mentioned it, right? This y-axis is simply there to give you the idea that the y-axis represents the functional value of X, not that where these y and x-axis meets is 0. No. So this x-axis goes towards infinity, and from the positive side it goes towards positive infinity. So the total area under the curve is 1. That is the total probability. So that's what's given here, right? So from minus infinity to plus infinity, if you consider the probability of X, it's 1. Since it's symmetric, from minus infinity to mu, the probability of X is 0.5. The probability of X in between mu and positive infinity is also 0.5. That is important to keep in mind when we are doing sums. Right. Now, we are talking about finding probabilities for normal distributions. So we have this standardized normal table. That is what we will be using when solving sums. So, for example, if you were told that the probability of to find the probability of the z value less than 2, and you found that it's 0.9772. How do you get this 0.9772 value? And what do I mean when I say probability of z less than 2? Now, z is, remember, the standardized normal distribution, right? So in a standardized normal distribution, the mean is 0, and you're asked to find the probability of z being less than 2. That is the area marked in red. So the value comes up to 0.9772. Now what I'm trying to teach here is, how do you get this value? So when you look at the table, you will see that your rows give you the values of the first decimal for the z, and your columns gives you the second decimal point for z. So in this case, you have 2.00, right? So you go and find 2.0 in your row elements, and then since you need 2.00, your second decimal point is also 0, you look at the first column. So the corresponding column and row gives you the value of 0.9772. So this 0.9772 is actually the area under the curve over here, right? So that is given by that. So that is how you figure out the value of this area under the curve where the probability of Z is less than 2. It is 0.9772. Right. So in other words, the probability from negative infinity for Z up to Z equals 2 is actually this value. Right. Let's put this in context. Let's have a look at an example. So you're told let X represent the time it takes to download an image file from the internet. And you're told this X is normally distributed with a mean of 18 seconds and a standard deviation of 5 seconds. You're asked to find the probability of X being less than 18.6 seconds. So the first thing that you should do is draw the graph pertaining to the X axis, right? That is the normal distribution. So you have the mean value, which is 18. You're asked to find the probability of X being less than 18.6. So up to 18, you know the probability is 0.5. Now you need to figure out what is the probability of this area. Or in other words, you can simply try to figure out the total probability up to 18.6. How do we solve this? Let's have a look at that. So how do we go about calculating this? First and foremost, let's convert these normal distributions into standardized normal distributions. In order to do that, let's figure out the corresponding Z value for this 18.6. So we use the equation for calculating Z, X minus mu over sigma. X is 18.6, mu is 18 and sigma is 5. If you were to calculate this, you will get 0.12. So if we were to draw the graph here, I'm going to draw the normal graph, and then here you have the mean mu, which is 18, and you're asked to calculate the probability of X being less than 18.6, which is this area, right? So I'm going to transform this into the standardized normal distribution such that my mean is now 0 and the corresponding data value of 18.6 is 0.12, and I'm asked to calculate this area under the curve. So when they tell me to calculate the probability of X being less than 18.6, when I transform into the standardized normal distribution, what I'm calculating is the probability of Z being less than 0.12. So if I do that, I need to now take my Z table and see what this particular 0.12 value is. Now how do I do that? I take my Z table here. Now it might not be clear, but 0.12. So the first decimal place is 0.1. I figured that out. And the second decimal place is 0.2. So this is the value I'm interested in. This says 0.5478. So that value gives me the direct answer. So the probability of Z being less than 0.12 is 0.5478. So this is the answer that is required. Right. Now, what we did first was, in that calculation, we figured out our Z value, right? The corresponding Z value for X equals 18.6. So the corresponding Z value we got as 0.12. Now why did we calculate the Z value? In order to have an idea about the standardized normal distribution, right? So you have the normal distribution like this with this information. You transform that to your standardized normal distribution. See the difference? In your normal distribution, you have the x points. In your standardized normal distribution, you have the z points, right? So the corresponding value of 18 is 0, since you have a look at the standardized normal distribution. The corresponding value of 18.6 is what we figured out here, is 0.12. Now, the original question asked us to find the probability of x being less than 18.6. So we have transformed it into a standardized normal distribution. Therefore, our question changes to figuring out the probability of z being less than 0.12. So we use the table and we see where 0.12 is. So the first decimal is 0.1. So we look at the row which says 0.1, and the corresponding column gives you the second decimal 0.02. So 0.12 gives me 0.5478, right? So 0.5478 is the probability that z is less than 0.12. So that is to say, from minus infinity up to 0.12, the area under the curve is 0.5478. And that is what they are asking me for. So that is one example. Let's have a look at another example. Now again, take the same example with this same mean and the same standard deviation. But the question is different. They're asking to find the probability of x being greater than 18.6. That's the important one. Previously, we were asked for x less than 18.6. Now we ask for what is the probability of x being greater than 18.6. Let's have a look at how we calculate this. So this question asks us to find the probability of x being greater than 18.6. So when I draw the normal graph with the x points and the mean as 18, I have my data point 18.6. What they're asking for is the area under the curve over here. So I transform this graph into my standardized normal graph, right, with z, and then I have my mean as 0. And this corresponding 18.6 value over here is given by 0.12, which we calculated in the previous example. So then when they ask me to calculate the probability of x being greater than 18.6, what I'm actually calculating is the probability of z being greater than 0.12. So how do I go about calculating this? What I do is I know the probability of z being less than or equal to 0.12. That is this probability. This is what we calculated before, right? So we calculated this as 0.5478. So the total area under the curve is 1. So if from 1 I deduct this 0.5478, I should get the area of this particular section, right? So what am I doing actually? What I'm doing is I'm deducting the probability of z being less than or equal to 0.12 from 1. That is 1 minus 0.5478, which gives me the answer as 0.4522. This is the area under this section, the probability of x being greater than 18.6. Right, just like before, we draw the normal distribution, but in this case we are asked to calculate the area under the curve of this part, which is marked in red. So I transform this into my standardized normal distribution, and when I do that, the corresponding z value of x equals 18.6 is 0.12. And what I do here is, now the original question is asking us to find the probability of x being greater than 18.6. I transformed it to my standardized normal distribution. Therefore, my question changes and I'm finding the probability of Z being greater than 0.12. Now, the problem is when I use the table up to 0.12, I know the probability, which is 0.5478. That's what I found out in the previous question. But what they're asking is not that. They're asking for the probability or the area under the curve marked in red. How do I figure that out? I use the previous knowledge that I had. The total area under the curve is 1. Why is that? The total area under the curve gives me the total probability. So the total probability is 1. So from 1, if I deduct this blue shaded area of 0.5478, I would get the area under the curve shaded in red. That's what I have done here, which gives me 0.4522. So in other words, when I'm trying to figure out the probability of Z being greater than 0.12, I can reiterate that and write it in this expression where I take the total probability of 1, right? So 1 here signifies the total probability. From that, I deduct the probability of Z being less than or equal to 0.12, which is given by the blue shaded area. And that gives me the answer as 0.4522. Right. Now let's have a look at another example with the same details. Here they are asking us to find the probability of X being in between two values. That is the mean and this other value of 18.6. Let's have a look at how we calculate this. So in this particular example, they're asking us to find the probability of X being in between 18 and 18.6. How do we go about calculating this? So again, I will draw my normal distribution with X. So I have my mean as 18 and the other data point being 18.6. What they're asking for is the area under this for this particular section. So if I were to transform this into my standardized normal distribution with Z, then my mean would be 0 and the corresponding 18.6 X value would be 0.12, right? So what we are asked to find is the area under this particular section. So before that, we need to calculate, since we already know the Z corresponding Z values, it is easy. However, if we were given the X values of 18 and 18.6, we had to first calculate the corresponding Z values. So the corresponding Z value for 18 would be 18 minus 18 over 5, which gives me 0. And the corresponding Z value of 18.6 would be Z equals 18.6 minus 18 over 5, which gives me 0.12, which I have already calculated since this is the same example. Now, then when they ask to calculate the probability of X being in between 18 and 18.6, what we are actually calculating is the probability of Z being in between 0 and 0.12. Now, how do we calculate this? So, what we are actually calculating would be, if you take a look at this particular graph, if we can calculate the area under the curve which comes up to 0.12, this area, right? If we can calculate the area of this and deduct this area, we would get the area pertaining to this shaded section. So how do we do that? So the probability of Z being less than 0.12, right? So that gives me the total area up to 0.12. From that, if I deduct the probability of Z being less than or equal to 0, this should be less than or equal to, that is the area pertaining to this section, I would get the shaded area. So the probability of Z being less than or equal to 0.12 We calculated that before, which was 0.5478. From this I deduct, what is the area pertaining to this? It's 0.5. Why is that? Because it's symmetric. So if it's symmetric, the probability to the left of the mean is 0.5. The probability to the right of the mean is also 0.5. So I use that particular fact in order to calculate the area for this shaded section, which gives me 0.0478. Right, so just like before, we calculated the Z values. The corresponding Z value of 18 is 0 and the corresponding Z value of 18.6 is 0.12. And when you draw the graph, so the x-axis, since the graph is the same, but the x-axis values gives us the normal distribution and the z-axis values gives us the standard normal. So the corresponding values are written down, the corresponding z values. What they're asking is for this. What is the probability that z lies in between 0 and 0.12? So how do I calculate this? Well, I can simply do like this. I calculate the area under the curve up to 0.12, and from that, if I deduct 0.5, I get the answer of the area shaded in red. Now, why did I deduct 0.5? Because I have to remember that we are talking about normal distributions. In a normal distribution, it is symmetric. And because it's symmetric, 1/2 of the area of the curve is 0.5. So I use that fact. So up to 0.12, what is the area under the curve? I use the standardized normal probability table. So 0.12 gives me 0.478, right? So from 0.478, which is the total area under the curve up to 0.12, I deduct 0.5, and that is what I have done here, which gives me the answer 0.0478. Now let's have a look at the third section under normal distributions, which is when you're given the z value, how do you figure out the x value? Now up to now, you were given the x values and you figured out the z value, right? That is, you were given the normal distribution. From that, you transform that into a standardized normal distribution and you figured out the probabilities. Now in this section, it is the reverse. You are given the standardized normal distribution and the details pertaining to that. Now you must transform it to the normal distribution in order to figure out the corresponding x value. So very simple. Your expression is given by this equation. Now why is that? Because your z value was given by z equals x minus mu divided by sigma, right? So if you just simply cross multiply, that is the first step. This is of course not needed, but for the benefit of those who do not understand, you cross multiply and then in the second step you take mu to your left hand side and you make x the subject, and hence you get this expression. So this expression is derived from the previous expression of pertaining to z, right? So from this we figure out the x value. So you would be given the mu value and the sigma value, and then you will have to figure out the z value from which you can determine the x value. So let's have a look at an example. The same example we will take with mean 18 and standard deviation 5. Look at how they ask the question. Find x such that 20% of download times, remember x represents download times, are less than x. So that is how they ask the question. Find x such that 20% of download times are less than x. So how do we go about this? Let's have a look at how to calculate it. So how do we calculate this? Well, first I have drawn the graph. Here I have drawn X and Z on the same graph, since only the scale differs, where my mean value of X is 18, the corresponding Z value is 0. Now they tell you have to find X such that 20% of download times are less than X. So when they say 20%, actually what they are saying is to calculate the corresponding value over here such that the area beneath that, right, up to that point would be 20% or 0.2 as I marked it here. Now the first thing I have to do is figure out what the corresponding Z value is, and from which I can figure out the X value, right? So first I have to figure out what the Z value is. How do I do that? I take my cumulative standardized normal distribution table, and then I see where I get the value of 0.2000 or the closest value to that. So when I go through all the values, I see that this is the closest value to 0.200, which is given by 0.2005. Then I see what is that, the corresponding row value and the corresponding column value, and that is given by minus 0.8 over here and 0.04 in the column. So that means this Z value is minus 0.84, right? So then I have to figure out what is my X. So now I figured out Z as minus 0.84 using my particular table, and then I also know that mu is 18 and sigma is 5. So in order to calculate X, what I do is I simply substitute it to this particular equation. So mu is 18 plus Z is minus 0.84 times 5. This gives me a value of 13.8. Now how do I interpret this 13.8? 20% of the values from the distribution with mean 18 and standard deviation 5 are less than 13.8. Now, according to what we did, first we need to figure out the Z value for the known probability. So how do we do that? So when you draw the graph, you were told to figure out the X values less than 20%, right? So the shaded area gives me 0.2, right? So 0.2, you need to go to a table and see where you get this 0.200 or the closest value to it. So when you check it, you will see that the corresponding value would be given by 0.84. Now you see, this is the difference between this sum and the previous sums. In the previous sums, you figured out Z and then you figured out this value. But here, you are given this value. Now you have to figure out the corresponding column and the corresponding row in order to get the corresponding Z value. So when you do that, you get the Z value as minus 0.84, from which you substitute it to the equation. You know your mu, it's given 18. You know sigma, that's also given, it's 5. You figured out Z, it's minus 0.84, from which you derive the value for X, which is 13.8. And how do you interpret this? 20% of the values from a distribution with mean 18 and standard deviation 5 are less than 13.8 seconds. And finally, let's have a look at evaluating normality. So you have to understand that not all continuous distributions are normal. So our chapter 6 covers not only normal distributions, but we will be talking about other continuous distributions such as uniform distribution and exponential distributions. So when you are given a data set, it's very important to figure out the normality, whether the data set follows a normal distribution, right? So one way of checking that is using this normal probability plot. So in this normal probability plot, what you have to keep in mind is if you get an approximately linear graph with a positive slope, right, you can say that your data is normally distributed. So what it would look like is something like this. So in this case, it is approximately linear, not exactly, but approximately. So in that case, you can say that your data would follow a normal distribution. However, there are cases where it can deviate from this. For example, if your probability plot, your normal probability plot is curved upwards like this, you would know that it is left skewed. We talked about skewness in chapter 3. So if you can't remember, please go back and have a look at what skewness is. And if the normal probability plot takes this curvature, you would say it would have a rectangular shape. And if it's curved downwards, you would say it is right skewed. So under normal distribution, we had a look at 4 sections. The first section was about normal distribution and standardized normal distribution. Then we talked about finding normal probabilities, the probabilities for normal distributions. And then we talked about finding the x value when the z value was given, that is the reverse of the second section. And finally, we talked about the normal probability plot. So this is what we will be talking about in normal distribution. Next up, let's have a look at uniform and exponential distributions. Right, so in this section, we will be talking about uniform distribution and exponential distribution. First, let's have a look at uniform distribution. So in uniform distribution, the important fact to keep in mind is the probability distribution has equal probabilities for all possible outcomes of the random variable. So that is what you have to keep in mind under uniform distribution. It has equal probabilities for all possible outcomes. Uniform distribution is also called rectangular distribution as well. So the function pertaining to continuous uniform distributions is given by this, where the functional value is 1 over b minus a if your continuous random variable lies between simple a and simple b. However, if your random variable is smaller than a or greater than b, your functional value is 0. Now, what is simple a and simple b? Simple a and simple b are the minimum value of x and the maximum value of x respectively. So the properties pertaining to uniform distribution, when you consider the mean of a uniform distribution, the arithmetic mean, you simply add the minimum value of x, which is simple a, and the maximum value of x, which is simple b, and you divide it by 2. And the standard deviation is given by this expression, where you take the maximum value of x minus the minimum value of x, you square it, divide it by 12, and you take the square root. So let's have a look at an example. So you're told the uniform probability distribution. You're asked to find the uniform probability distribution over the range where x lies between 2 and 6. Now let's have a look at how we calculate this. So how do we calculate this? Well, it's very simple. First, let me draw the graph pertaining to this uniform distribution. You have x and you have f of x, right? So between 2 and 6, you have a uniform distribution, right? So we need to figure out first and foremost what the value here is, right? What the functional value here is. How do we figure that out? Now this is simple a, that is the minimum value of x, and this is simple b, this is the maximum value of x. So f of x is given by 1 over b minus a. So b is 6. So 1 over 6 minus simple a is 2. So when you calculate that, you would get f of x as 0.25 for the values of x being in between 6 and 2. If not, it would be 0. Right? So that is why I have 0.25 uniform distribution drawn here. Otherwise, the functional value is 0. So the mean value is given by a plus b over 2, which is simply 2 plus 6 over 2, that is 4. And the standard deviation is given by b minus a squared divided by 12, the square root of that, which is 6 minus 2 squared divided by 12, the square root of that. And if you use the calculator, you will get the answer as 1.1547. So what I did was I calculated the functional value. Simply it's 1 over b minus a, which is b is the maximum value of x, which is 6, minus the minimum value of x, which is 2. That gave me 0.25. So that is the functional value. So when I draw the graph for a uniform distribution, the x values between 2 and 6, the probability is uniform. It remains the same. So this value is 0.25. So the mean is given by a plus b over 2, and you get 4. And when you substitute in the values for b and a over here, you get the standard deviation 1.1547. So in the same example, if you were asked to find the probability of x being in between 3 and 5, how would you calculate this? Well, you have the graph, so you know the functional value of 0.25. You simply calculate the area under the curve. And how do you do that? It's a rectangle, and the difference between these 2 points is 2, and the height is given by 0.25. So the area under the curve, or the area of this rectangle, would be 2 times 2 is this difference times the height, 0.25. So that is how you get 0.5. So there's a 0.5 probability of x lying in between 3 and 5 when x is uniformly distributed. So that is a small brief introduction to uniform distribution. Let's also have a brief introduction into exponential distributions. So this here, the exponential distribution model, is used to model the length of time between two occurrences of an event. That is what you have to keep in mind. It is a model used to measure the length of time, or model the length of time between two occurrences of an event. So for example, you can take the time between trucks arriving at an unloading dock. So you see, it talks about time between trucks arriving at an unloading dock, time between transactions at an ATM machine, and then finally time between phone calls to the main operator. So this is defined by a single parameter lambda, and the probability that an arrival time is less than some specified time x is given by this equation. So what is x? It is any value of the continuous variable, some value of the continuous variable, and x can take any value from 0 to positive infinity. So we are trying to find the probability of a particular arrival time being less than x, and that is given by the expression 1 minus e to the power minus lambda x. So what is lambda? That is the population mean number of arrivals per unit. So let's have a look at an example. Customers arrive at the service counter at the rate of 15 per hour. The question asks, what is the probability that the arrival time between consecutive customers is less than 3 minutes? Now let's see how we calculate this. So when you're given a question like this, first you need to read the question very well and understand Okay, you are using the exponential distribution for this. That is very important to understand. And then you write down the details that are given. So you're told customers arrive at the service counter at the rate of 15 per hour. So that tells us that our lambda is 15. This is per hour. And they are asking us to calculate the probability of the arrival time between consecutive customers is less than 3 minutes. So let's convert this minutes, 3 minutes, into hours. And if you do that, you will get 0.05 hours. Now why do I do that? Because it's easier for me to do the calculation when it's in the same units. Since lambda is also 15, the rate is 15 per hour, I convert this minutes also into hours. So then what do? They're asking for the probability of the arrival time being less than 3 minutes. So in hours it's 0.05 hours. So the exponential distribution is given by 1 minus e to the power minus lambda x. That is 1 minus e to the power minus lambda is lambda is 15 times x is given by 0.05. Right, so this is multiplication. Don't mix this x. This is x, this is multiplication. So that is the answer you would get as 0.5276. So how do you interpret this? So there's a 52.76% chance that the arrival time, right, the arrival time is less than 3 minutes. There's a 52.76 chance. Right. So what did we do first? We write down the details. So it was told to us that customers arrive at the service counter at a rate of 15 per hour. So that tells us our lambda is equal to 15 because it gives us the mean number of arrivals per hour, which is 15. We are asked to find the probability that the arrival time between consecutive customers is less than 3 minutes. Now let's convert all the units into one standard unit. So rather than having it in minutes, I'll convert this 3 minutes into hours. And that's how I got 0.05 hours. Why did I do that? Because my lambda is in hours. It's in per hours. So the probability of my arrival time being less than 0.05 hours, or in other words 3 minutes, is given by 1 minus e to the power minus lambda is 15 times x is 0.05, and that gives me 0.5276. So what is this 0.5276? That tells me that there's a 52.76% chance that the arrival time between successive customers is less than 3 minutes. So that is an example for exponential distribution, where you look at, it's a model to look at the time between two consecutive events. Right, so that was a brief introduction to two other different types of continuous probability distributions other than for the normal distribution. So the final area under this particular chapter is the normal approximation to binomial distribution. Now, if you remember, we talked about binomial distribution under chapter 5, and binomial distribution is a type of discrete probability distributions. So you may wonder why we are talking about this under chapter 6, where we are looking at continuous probability distributions. But if you look at the topic, it says the normal approximation to the binomial distribution. So let's see why we have this particular normal approximation. Right, so a binomial distribution is a discrete distribution. So we know that, right? So it arises from a counting process. The issue with this binomial distribution is when our n, or sample size, gets larger, the calculations become more difficult. Why is that? Because if you remember the function pertaining to binomial distributions, you had a counting process where you considered NCX, right? Combinatorics. So when that n or the sample size gets bigger, it's very difficult for you to calculate NCX. So therefore, the calculations pertaining to binomial distribution becomes tedious. So that is why in such a situation, when n gets larger, you use the normal distribution approximation for this binomial distributions. So how do we do that? So consider capital X to be a binomial random variable, which means capital X is a discrete random variable. And the probability of X being equal to C is non-zero for any C, 0, 1, 2 up to n. Because if you remember, in a binomial, for a binomial variable, there are only two events that can occur. For example, a product can be defective or not defective, right? So the probability cannot be 0 for one event. That means only one event will occur. For example, if a product is going to be defective, the probability of a product being defective is 100%. That means there is no probability or zero probability of a product being not defective. That cannot occur. For a binomial random variable, two events should be there. So that's why this probability of X equals C is non-zero. Now take W to be your normal random variable, or in other words, consider W to be your continuous random variable. So in this case, probability of W equaling C for any value C is 0. Why is that? Because W is a normal random variable, and if you remember when we were talking about normal distributions, any single individual value, the probability assigned to it is 0. Because under normal distributions, the area under the curve for any single value is 0, right? So to approximate this, what do we do? So if X is binomial and W is normal, we approximate it by this. So where you take the probability of W to be in between that particular C value minus 0.5, that particular C value plus 0.5. So you may ask, what is this 0.5? That is the particular continuity adjustment. So when can we use the normal approximation? So this can be used under two conditions. N times pi should be greater than or equal to 5. N being the sample size and pi being the probability assigned to the particular event of interest. And n times 1 minus pi should also be greater than or equal to 5. And just a small recap, a mean of the binomial distribution is given by n pi, and the standard deviation is given by n times pi times 1 minus pi, the square root of that. So let's have a look at an example as to how we use this. So you select a random sample of 1600 tires from a production process with a defective rate of 8%. Now you want to calculate the probability that 150 or fewer tires will be defective. Now when you read this, you understand that you're talking about tires and you're given the defective rate of 8%. So you know 92% are not defective. So you have an understanding, okay, the binomial distribution is used here. However, the issue is the large sample size of 1600 tires. So then since you have learnt about the normal approximation for binomial distribution, you use this. So let's have a look at how we calculate this. First we calculated the mean, which is n times pi. N is 1600, pi is the probability of a product being defective, which is 8%, hence 0.08. You get the mean as 128. Standard deviation is n times pi times 1 minus pi, and the whole thing, you take the square root of that. You get 10.85. So you consider capital X, which is the tires being defective, as a normal random variable, so that what you want is the probability of your capital X being less than 150.5. So how do we do that? Well, rather than calculating x, we transform this into the standardized normal form, right? So when you're using normal approximations, you can use the standardized normal distribution. Hence, you consider the probability of z being less than 150.5 minus the mean divided by standard deviation. And you get 0.9808. So what is this 0.9808? We approximate the probability of finding 150 or fewer defects as 0.9808. So that is an example of using this approximation, normal approximation to binomial distributions. So throughout this lesson, we talked about a lot of things. We talked about normal distributions, and under which we talked about 4 sections. We talked about uniform and exponential distributions, 2 other types of continuous distributions. And finally, we talked about the normal approximation to binomial distributions. So the chapter summary, we talked about presenting key continuous distributions, that is normal distribution, uniform distribution, and exponential distribution. We found probabilities using formulas and tables, recognized when to apply different distributions, applied distributions to decision problems, and finally, approximated binomial probabilities using the normal distribution. So this is the chapter summary. And also a quick reminder of the reference book. Please make sure that you download this book and refer to it. There are many problems given in this particular book. All of these lessons are based on this particular book. And that is it for today. I hope you understood about continuous probability distributions. What I would like you to do is go back in the video and make sure you watch it again and see which areas you do not understand. And hopefully, once you watch it twice, 2 or 3 times, you'll get a basic understanding about continuous probability distributions. Thank you very much, and I hope you have a productive day.